series for e to the x. Can anybody help him out? Yanni, what is it?
1
Yep.
plus x.
Yep.
Plus x squared over 2 factorial.
Mm-hmm.
Plus x cubed over 2 factorial.
Right? You have to know that cold. So what do you plug in for x to get this thing? What do you plug in? 2. If you plugged in 2 for x, you'd get e squared, right? Equals 1 plus what? 2 plus 2 squared over, I'm going to try to do this in 2 different colors here. Like this, right? Hey, is that the exact same thing?
Yes.
So therefore, what does this equal? E squared. That sum is e squared.
Oh.
It is e squared. When you plug in 2 for x, that's what you get, e
So
squared.
you don't need to do any ratio test, right?
No, it's not asking. By recognizing each series. So for the second one, what does that one look like almost?
Sine.
Looks like sine evaluated at what number?
Pi.
What is
No.
1? Just sine. It's of 1. Plugged in 1 for x. What is sine of x? 1 minus what? X cubed over 3 factorial plus x to the 5th over...
Doesn't sine start with x?
Sorry, x, yes. Thank you. Plus, minus x to the 7th over 7 factorial. Oh, look, what happens when you plug in 1 for that? You get the same thing, so it is sine of 1. What's 37 look like?
1 over 1 minus x.
Yeah, it looks like 1 over 1 minus x when x is what? When x is 1/4, because 1 over 1 minus x is the really, really straightforward one. What's that one? 1 plus x squared plus x cubed. So what is that? That's when x is 1/4. So you plug 1/4 into here, and what do you get? 1 over 1 minus 1/4? What does that equal? What's that equal? 4/3. Well done.
Wasn't that
So this is 4/3.
is that a geometric series formula?
It is. Yeah. It is also a geometric series. And what's the formula for adding together an infinite geometric series that has a ratio less than 1? 1 over 1 minus r. Oh, look. That's what we just did. Sweet. So cool. Which type is that? What formula do we use? No, it's doing this thing. Hold on a sec. 6. What did you say? 1 plus x to the what?
Negative 1.
Yeah, so, but you use that formula. So what's it asked? First 4 non-zero terms? This is just 1 plus x to the what power?
Negative
1/2. So p is negative 1/2. So you're expanding that based on, what does this equal? 1 plus x to the p. Can someone tell me what that equals? You have to memorize this one. Anybody remember? What is it, Soma? 1 plus what? 1 plus px plus what? X what? Yep, and then what's the next one? P times p minus 1, p minus 2 over times x cubed. Exactly. Exactly. So in this case, all we're doing is plugging in negative 1/2. That's all we're doing. We're plugging in negative 1/2 for p. So what do we get? 1 plus, I can almost write a 1. 1 plus x to the negative 1/2 is going to be equal to 1 minus 1/2 x plus what? Negative 1/2 times negative 3 over 2 over 2x squared. Negative 1/2, negative 3/2, negative what? Over 3 factorial x cubed. That would be the first 4 non-zero terms. Now on a test, I would expect you to simplify that a little bit. On a test, I would expect you to simplify it. So what do you get? 1 minus 1/2 x. And then what do you get here? You get plus what? 3 over what? 8x squared. And then you get minus what? 15, 8 times 6 is minus 15 over what? 48 x cubed. I think that's right. Is that right? Did I do the math right? Is that okay? Can I simplify that a little bit? Yeah. Hold on, let's finish what I'm talking about and then we can go to your question. Can we simplify that a little bit? Say yes, everybody, because we love fractions and you're conscious still. I know it's hard. It's the last thing on Friday. Divide by 3, you get what? 5 over what? 16x cubed. So what are the first 4 non-zero terms? There they are. Those are the first 4 non-zero terms. About the point A. Okay, so you need to remember the formula. What is sine of x. Can someone remember what the sign of x is? What is it? Any?
X minus x cubed over 3 factorial.
Yep.
Plus x to the 5 over 5 factorial.
Mm-hmm.
Minus x to the 7 over 7 factorial.
Right? And you're doing it around what?
0.
No, and this one you're doing it around
Pi over 4.
pi over 4. So what's the only thing that changes here? So what does it change to? Come on, you all did the homework. What's it change to?
1
1 minus pi over 4. That's sine x, right? Okay.
1 plus 1 pi over 4. It's just negative pi over 4.
Pi over 4. So you actually have to construct this. So you write out the derivatives, which you know, and luckily sine is what? Cyclical when you do the derivatives, right? So what do we have here? F of x is equal to sine x. What is f of pi over 4? What's sine of pi over 4? What is it? Root 2 over 2? Oh, it's negative pi over, so it's going to be what? Negative root 2 over 2. Nice. And then you have f prime of x is equal to cosine of x. Not equals. What's f prime of negative pi over 4? Root 2 over 2. And then f double prime of x is negative sine of x. F double prime of negative pi over 4 is going to be what? Hey, it's a lot of these. Do the third one here. You get what? Negative cosine of x. So f triple prime of negative pi over 4 is what? Negative root 2 over 2. And then you put this all together, right? You put this all together. So we know that sine of x around, this is at around negative pi over 4, is going to be what? What's the leading one going to be? Negative root 2 over 2, right? Plus what?
2 root 2 over 2.
2 root 2 over 2? No, it's just root 2 over 2. Root 2 over 2 times theta what? Plus or minus root? Plus or minus? Plus. Why is it plus? X minus a. Right, the a is negative. So then what's the next one going to be? Plus? Root 2 over 2. Yep. Yeah, so times. You have to do a fraction. I'm just putting them out front here. And then it's theta what? Plus pi over 4 what? Over 2 factorial. And then what's the last one? Minus what? Theta to the third over 3 factorial. There they are. So where did they all come from? Well, this one went right there. This one went right there. This one went right there. And this one went right there. That's where they all came from. So what do you have here? Over 1 factorial. Yay, there it is. There are the first 4 non-zero terms. Yes?
The question before asked for just...
Must memorize them. So theoretically, I could ask you this one, e to the negative x squared. How would you get e to the negative x squared? If you want, plug in what to what?
Negative x squared to x.
Into x so it's going to be 1 plus that thing squared over 2 factorial plus that thing cubed over 3 factorial. And what do you plot there?
Negative x.
Exactly, negative x squared. So negative x squared goes into all of these. Can you simplify those a little bit? Absolutely, but straight substitution works really well. If you are trying to build a Taylor series that looks really similar to one you know, you can use substitution like this. Yay, that's pretty cool. Now, what you generally tend to do is you tend to write it, instead of saying x equals and x equals and x equals, change it to like e to the y, and then let y equal negative x squared. That's what we just did. Notationally, that makes a lot more sense. Try to avoid doing things like this. X is equal to this, x is equal to this, x is equal to this, and then these are all different x's. Do you understand what I mean? Yeah. You just change the letter. Does it matter what letter you use to start with? No, just change it. It's easier that way. What does this one look like? What does it almost look like? It looks like 1 over what? What's the one we know? We know 1 minus x. So how do we change this to 1 minus something? 1 minus what? Negative x squared, right? What does this one equal?
I mean 1.
Sorry. Sorry. What does 1 over 1 minus y equal? 1 plus plus y cubed, right? So what are we going to let y equal?
1 over x.
Nope. We're going to let y equal what?
Yeah,
Negative x squared. So all we do is we plug in negative x squared into there, and do we get the answer? Absolutely. So this is just straight substitution. You get 1 minus x squared plus what? Negative x squared squared plus negative x squared to the... Can you simplify that? Yeah, 1 minus x squared plus what? Minus... Yeah, dot, dot, dot. So direct substitution works. You just need to recognize what you are close to. You have to recognize what you are close to. In this case, you were really close to 1 over 1 minus x, which you know. What's the only thing that changes right here? It looks more complicated. Is it more complicated? No, it really isn't. What do you plug into what here? You plug in what? Sine of...
Wait. No.
Oh, I'm sorry. This one, I went up too far. I was like, trying to leave you with one that looked better. Sorry. You plug in sine of theta for x in the Taylor expansion of e to the x. Exactly. So you know that e... Oh, I keep on hitting with my bottom hand, sorry. You know e to the x is equal to what? 1 plus x squared over... Yeah, x cubed. I know, it gets really boring after a while, but it should be boring because then it'll be fast. So what does e to the sine theta equal? 1 plus sine theta plus sine theta squared over 2 factorial plus sine theta cubed over 3 factorial. Nice. First 4 non-zero terms. It keeps going. Awesome. So can you plug functions in? Absolutely. Sometimes things are a little bit more hidden. Sometimes things are a little bit more hidden. So this one, yes.
So that one should we like expand sine?
No, stop. Yeah, stop. That's fine. 做完了. Done. Okay? We're good right there. I don't want you using double half angle square things. Just leave it. This right here, though, it's hidden a little bit. There are 2 paths we can take. 1 over 1 minus x squared looks like 1 over 1 minus x, right?
Yeah.
But is it?
No.
So what do we have to do to the bottom first? What'd you say, Nam?
Expand it.
Yeah, let's expand it. So this is 1 over 1 minus what? 2x plus x squared. We want it to fit this form, 1 over 1 minus y, right? That's the form we want to fit. So how do we rewrite that to fit that form? 1 over 1 minus 2x minus x squared. Be super careful.
Why?
Because without it, it wouldn't be the same. The negative distributes in, right? So in this case, we say 1 over 1 minus y is equal to what? 1 plus what? Y plus y squared plus y cubed. So in this case, we're going to let y equal what? 2x minus x squared. So what do we end up with? We end up with 1 plus 2x minus x squared plus 2x minus x squared squared plus 2x minus x squared what? Cubed. So that's one way to do that one. Do you agree? That's one way to do it. But what did we say? What did we say 1 over 1 minus x was equal to? We did it a couple days ago, and I'm just changing the letter. Well, that's equal to x plus what? Sorry, 1 plus what? 1 plus x squared plus x cubed, right? If 2 things are equal, can you square both sides? Yeah, if a equals b, does a squared equal b squared? So what could we do to both sides? So what do you end up with? 1 over 1 minus x squared is equal to that thing, right? Here's the thing. What we really just proved, which is really cool, the really cool thing we just proved is that, in fact, sorry, my calluses are making it very hard to use this. This thing is equal to what? That thing. That's pretty neat. We just show that this, when you expand it out, turns into this thing, which isn't really super helpful, but it's kind of cool. Does this automatically look like that? No, it doesn't. But it shows you 2 things. You can either multiply it out and kind of force the 1 over 1 minus x, or you can square both sides and still build it. I call this like mutating. If you're really close, you can do it. What about square rooting? Should we ever square root things?
No.
Be really, really careful about square rooting things, because if you square root things, you can introduce false positives. Like, what's the square root of 25? Plus or minus 5, right? 5 doesn't necessarily equal -5. You can create false positives. This is pretty cool, though. At least I think it's pretty cool. Okay, so I would like you to find a piece of the board, everybody, with somebody you haven't worked with lately, and try them. When you did this out, you found out that you knew, in a pretty straightforward fashion, 1 over 1 plus x squared, you figured out that it equaled what? 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th. Do you agree with that? Is that right on the board?
Yeah.
But you also, from AB calculus, you know that this, what is that? That's the derivative of what? Tan inverse, right? So how do you go from that to tan inverse? You take the integrate. You integrate to get from the derivative to the function. So if you integrate on the left, you have to integrate on the right. So you integrate the right-hand side, and you get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. So do you agree with this statement right here? Who agrees with that? The highlighted yellow. Is that good? Did I write it right?
What about C?
What about what? Sure, plus C. Sure, plus C. You know that tan inverse of 0 is 0, therefore C has to be 0. So that is 0 right there. Why is this super cool? Why is this super helpful? Well, here's the leading question. Use this series for arctan to estimate a numeric value for pi. This is really cool. And the hint I'll give you is this. Tan inverse of x equals pi over 4. What does x equal? Raise your hand when you know it. Don't say it out loud. Raise your hand. The inverse tangent of what is pi over 4? Raise your hand when you got it. Ian, what is it? Nope. Close. Close. Tan inverse of what is pi over 4? Yeah. Stephen? 1. 1.
Oh, yeah.
The tangent of pi over 4 is what?
Yeah.
1. So in this case, x is 1. Do you agree with that?
Yeah.
Okay, so here's the thing. So you now should theoretically remember tangent of 1 is pi over 4. What does that tell you? What is 4 tan inverse of 1 equal to? Pi. So what can you plug in up here? What does this tell? Tan inverse of 1 is equal to 1 minus a third plus a fifth minus what? A seventh. So if we multiply it times 4 on both sides, what do we get an approximation for? Pi. We just proved a way to get arbitrarily close to pi. So if you wanted to find an estimate of pi to an arbitrary number of decimal places, 1 minus a third plus a fifth minus a seventh plus a ninth minus an 11th plus a 13th, multiply that by 4, and what do you have? Pi. We just used Taylor series to estimate pi. Pretty cool. Okay, I think it's pretty cool.